continuing along. As it turns out, electrons can spin too. So I'm kind of shifting gears here, okay? And so, we've described this picture of like some center of mass and some electron spinning around that center of mass, okay? But also this electron itself can rotate about its own center of mass. So this is much like our solar system picture, right? Where we've got, here's Earth spinning around 24 hours in a day, but then also 365 days to make it all the way around. So what that means is there's actually two contributions of angular momentum as a result. There's the orbital angular momentum, right? But then there's the electron spin angular momentum, okay? This is going to become really important in spectroscopy. And a result, what's really cool about this, if you look at the hydrogen atomic emission spectrum, you have to have a very, very precise spectrometer to do this. But if you were to zoom way into the red line at 656.3 nanometers, you would actually see that it's a doublet. And the reason why that's a doublet is because, recall, in hydrogen, it's got one unpaired electron, okay? So if its spins are correlated, so in other words, if the picture looks like this, that's going to be a system, or excuse me, there's going to be a specific energy associated with this system. But if it's spinning the other way, I'll draw that picture down here. So let's say it's still orbiting around in this dimension, or in that orientation, to give you orbital angular momentum that points in that direction. But let's say it's a downward pointing electron, right? So it's pointing, so it's spinning the opposite direction and pointing down. The way that those two angular momentums couple create different energy transitions. And as a result, with this unpaired electron system, you see a doublet due to the electron orbit spin coupling, is what we call that. And we're going to come back to this in more detail in spectroscopy, okay? So the way that this was first discovered was in the very famous Stern-Gerlach experiment, where they took silver atoms, okay, and they did they ionize these silvers? I want to say that they had to ionize them to get them to do this thing here. Let's see. Well, in any event, we looked at silver atoms because, as it turns out, silver has one unpaired electron. I'm looking for my periodic table right now. Let's see here. Yes, it had to be silver atoms because if you look at silver plus, right, the 4s or 5s2 fills over and fills the shell. So we know that then that's really, right, 5s1, 3d, sorry, 5s2, 3d9, okay? So if electrons weren't spinning, okay, so what they did in the Stern-Gerlach is they had this big magnet north-south pole, okay? And if electrons weren't spinning, then what you would expect is as these atoms expanded into this evacuated region, so this side was vacuum, which is going to give you that throttling expansion, okay? Then what they would have expected is, a silver atoms like would be all over the place. Like they're, you would see like a spread of them hitting that phosphorus screen. But that is not what happened. When they separated those atoms in a magnetic field, they got atoms that would either hit the screen right there or atoms that would hit the screen right there. And those results are what led them to conclude that electrons themselves must also be spinning. And so there's loads of examples that we'll see in spectroscopy that gives evidence of these kinds of things, these doublets, right, that show us that electrons spin. And that their spin, angular momentum, couples with their orbital angular momentum. which is very cool, all right? So, and of course, we can come up with the same situation in this vector model. So as it turns out, so the spin magnetic quantum number, ms, is given by s minus 1, all the way down to negative s. As it turns out, there's only one quantum number for electrons, and that's s equals 1/2. We can come up with spin quantum numbers for other particles as well, like photons or neutrons or protons, and they have different values of s. S equals 1/2 for electrons. And because ms takes on all values s minus 1, negative s, this means for an electron, ms can be plus or minus 1/2, okay? And just like we saw with orbital angular momentum, electrons are also suspect to the same Heisenberg uncertainty principle. The z component of their vector is given by ms h bar. The projected length is given by s times s plus 1 h bar. And we can make the same picture right here that we just did. And they have the same conical representation of their angular momentum. All right? So I've been talking for quite a bit, so I'm going to wrap that up, and I'm going to record one more very quick short lecture after this that's going to be kind of like a wrapper for this whole chapter. Okay?